Ipshita of IEEE RAS Northcap University Student Branch in collaboration with Verena Faiz of IEEE Al-Safwa High Institute of Engineering Student Branch. We proudly present you today's webinar on virtual interaction with collaborative robot Sawyer by Rethink Robotics. Today, we will have 4 guest speakers with us. Mr. Florian Nadolny, who will give the overview of the webinar, Mr. Hans Buczynski, who will give the basics of AI and ML overview, and Mr. Dennis Trapp and Ms. Jessica Rosing will present you the Sawyer and the functions of Sawyer. Our first speaker would be Florian Nadolny. He is a regional sales manager of Dash. He is an electrical and information technology engineer and is responsible for company sales in Germany, Austria, and Switzerland. The next speaker we have is Dennis Trapp. He is an application engineer, formation as a machine technician, and an expert of Sawyer and cobot application. He evaluates all applications of Sawyer that can be used, as well as evaluating solutions in case of difficulty. Third speaker we are going to have is Mr. Hans Buczynski. He's an innovations manager and a mechatronics engineer. He scouts and researches the latest trends in robotics, automation, AI, etc. in R&D and in market and contemplate how this affects new market and their application, their product, and their customer needs. Next, we have Ms. Jessica Rousing. She's a project manager and a management assistant. She manages all the projects on the commercial departments at Rethink Robotics, which are related to structure, strategic, or growth topics. We welcome you all. Thank you so much for attending as a guest speaker. Now I would like Verena to introduce herself.
All right, thank you for the introduction, Ms. Data. Thank you for the...
Also, actually, we'll be posting a feedback form in mid-webinar. Do fill this form to get an e-certificate. Now, I would like Mr. Florian Nadolny to introduce the company and give the overview of the event. Over to you, sir.
All right. Thank you very much for the introduction, Ms. Data. Thank you very much for having the chance to speak here today. Before I start, let me share my screen with you. Just a second. So I hope everybody can see my PowerPoint presentation now. I hope everybody can hear me well.
Yes, loud and clear. Thank you.
Yeah. Perfect. All right, then welcome everybody to today's webinar about our collaborative robot Sawyer. First of all, I would like to introduce myself. My name is Florian Nadolny, as already mentioned. I'm 39 years old. I'm studied electrical and information technology engineering at the University of Applied Sciences in Aschaffenburg. Aschaffenburg is a smaller city in Germany, which is approximately 30-40 minutes by car away from Frankfurt Airport, just to give you an idea. And well, right after the time or my time at the university, I started to do sales of high complex industrial products. My main focus was the industrial camera business. And I basically did this for around about 14 years. Since April this year, I'm employed by Rethink. I'm part of that successful group. And as already mentioned, I'm responsible for our sales in the German-speaking part of Europe, which is Germany, Austria, and Switzerland. That's all I would like to say about myself. Let's talk a bit about Rethink Robotics. Let's talk about who we are. Rethink Robotics, we are a German company, a GmbH, which was founded 3 years ago, so in 2018. And right now we have 55 employees. We are a successful and a really fast-growing company. Just to give you an idea, in November, December last year, we've been only 20 people. So within 6 months, we more than doubled the number of employees. Our headquarters are in Bochum. Bochum is also a city in Germany. It's close to Dortmund, close to Essen, in the Ruhrgebiet of Germany. And Rethink Robotics, we are a manufacturer. We are the manufacturer of Sawyer. Sawyer is the robot you can now see on the right side of the slide. So the red robot with a tablet on top and with the blue eyes. And Sawyer is the only product we offer at the moment. It's been in the market since a while. And an important information for you is as well that we have a development agreement with Siemens Technology Accelerator and Siemens Corporate Technology. And together with Siemens, that large and successful company in Germany, we are currently developing a new robot family. I cannot tell you more about it, but there's a lot to come. Rethink Robotics, we are part of the Hahn Group, and that gets me to the next slide, the Hahn Group history. The Hahn Group is a group of around about 30 companies, and we have a really long history. It goes back to 1992. At that point in time, Hahn Engineering was founded by our former CEO, Thomas Hahn. At that time, the company had 3 employees in total. And as you can see on that slide, each year there came more companies into the group, companies with different knowledges, companies with different sizes, and so on. And all companies in that group are focused on industrial automation, are focused on robotic solutions, and are more or less machine builders. So they deliver complete machines. They are system integrators, so they are able to deliver complete solutions. The reason why I say this is that our role inside that Hahn Group is a bit unique because we are the only product manufacturer. As already mentioned, we are the manufacturer of Sawyer, our collaborative robot. And this product we produce is used in the solutions and in the machines of our, let's say, sister companies. In total, the Hahn Group employs 1,600 people roundabout, and we are, we have locations in 14 different countries. That means we are, represented worldwide. All right, on that slide, I only want to give you some insights. On the upper left side, you get an impression of the entrance area at our headquarters in Bochum. You can see some demo applications on that image. On the upper right side, you can see some of our employees. That picture goes back to, I would say, September, October last year. So there are only 20 people at that image. I think it's time for a new photo. Nevertheless, on the lower left side, you can see Sawyer, our collaborative robot, in an application. Sawyer is part of the Cobot Cafe on that picture. And basically, the one who wants to have a coffee just types it in the tablet on the left side, and Sawyer is doing the rest. Let's say it's giving you a cappuccino or a coffee or whatever you like to have. So kind of service robotic application. The other 2 images on that slide show our production part of our headquarters. So yeah, just feel free to get an idea how it looks like. All right, that's basically it. What I would like to say about Rethink Robotics. I have one final slide for you, and this is the agenda of the webinar today. And we have 3 topics today. The first one more or less already happened because I already introduced Rethink Robotics to you. You know now who we are. And the second topic, this is something you do not know yet, is our product. You do not know who Sawyer is. So the second topic of the agenda today will give you some more information about Sawyer itself. The third part today, and more or less the most important part today, is an introduction by my colleague Hannes Kuczynski. He will give you an intro to artificial intelligence as well as machine learning. Yeah, stay tuned. That's the third part. I would like to hand over now to Dennis Trapp and Jessica Reusing, so two colleagues of mine, who will tell you a little bit more about Sawyer. Jessica Reusing, she's our project manager, as already mentioned at the beginning. She will be more or less the voice of the next part, so the speaker. Dennis Trapp, our application engineer, you will see him really collaborating with Sawyer. You will see him live on screen. He will show you some pick and place applications, etc. Dennis is really an expert for Sawyer. He's an expert for cobot applications in general. All right, that's basically my part today. Again, thank you for the chance to speak here today. Thank you for participating, everybody. And yeah, I would like to hand over now to Dennis and Jessica. Thank you.
Thank you, Florian. Okay, so after this nice introduction, I will start explaining to you what actually makes Sawyer so special. So Sawyer for us is more than a machine. Sawyer is a colleague and a friend, and you can tell this by simply looking into his blue eyes that Florian already mentioned. Just like a friend, Sawyer would never hurt you or put you in danger. And this is basically due to a patent safety solution, which is able to measure external forces. But more than this, you also see those black covers around the joints. And because they are very round and soft, even if there's a collision, there's no possibility to hurt yourself. There are no harsh edges or anything else. And so Dennis will now use Sawyer to show you what happens in case of a collision. He will start a very basic moving program and then put himself into the path of the robot. You see, there's not a lot of force behind. He can simply stop the robot or even push the robot away. So nothing happens. You can really work directly. Besides Sawyer, you don't need any sensors or any other security surroundings or expensive equipment to protect the co-workers. You can cooperate just like with a human being. But more, Sawyer is also an acrobat, and this is due to the 7 axes it has, which gives him more degrees of freedom than many other robots and cobots have. And yeah, therefore, Sawyer is able to perform movements also in very narrow and confined spaces, making use of a range of motion of approximately 1 meters. And for those who want to know it more precise, 880 millimeters. But all these features would not be so powerful if Sawyer was blind, and therefore we have one camera on the top. So, Dennis is going to show you the camera right there. And this top camera is supposed to watch the environment, and the other camera that Dennis just showed us on the flange is to actually perform tasks such as a pick and place application. So this is leading me to the next point, because we would like to show you that it is very, very easy to program the robot. Sawyer itself, obviously, something you can use for your pick and place application. Dennis, can you show us the tin for the sweets that we are going to pick? There you go. Thank you very much. And yeah, you need a co-worker, a human being who is programming Sawyer. So let's just start. First, Dennis is going to show or to program Sawyer starting position. And therefore, Dennis presses the so-called 0G button, and 0G stands for zero gravity, and now simply moves the arm to the desired position. And below the 0G button is another button called Action button. And right there, he's able to add a so-called move to node in the program by simply pressing this button. And now that the robot has learned the starting position, we are again moving the arm using the 0G mode to the next desired position. And now we save the new position, again using the action button and saving it as a move to node. Now we are implementing another feature, which is making it very intuitive to work with Sawyer. And this is the feature we call touch and go. And it works basically making use of the external forces that Sawyer is able to measure. I think I mentioned this already in the beginning of this talk. So we will program a so-called wait until node right before the first moving command. And in this example, we will simply define a force of 15 Newton and tell the robot that the next program should not start until it measures a force bigger than 15 newtons. And maybe Dennis can demonstrate how it is when he gives Sawyer a touch. So very easy. You push the Sawyer, the robot, it registers a force and then starts by
Jessica,
working out the program.
Sorry to interrupt you. Dennis is not visible for everybody. I think we need to pin his screen or something like that to spotlight him or.
Mm-hmm. Okay, someone is saying it's pinned now.
No, it's visible. Okay, all right.
Okay, maybe you can give us some feedback, because if you didn't see the presentation so far, maybe it makes sense to repeat. What do you think, guys? Okay, then we will just continue. Okay, so we have now programmed touch and go feature, and now we would like to continue by actually programming a very simple pick and place application. So what we do now is we bring Sawyer's arm right above the part we actually want to pick, again using the 0G mode. And now we are using another button, the grasp button, to access the so-called grasping menu. And there we choose a basic grasp. Once we have done this, we are again using the 0G mode to bring the arm in the position where the part shall be placed. And again, using the grasp button, we are going to tell the robot that he has to perform the basic place. And that's already it. So let's start the program and see how Sawyer performs the pick and place application. There you go. Obviously, this is a very basic pick and place. We didn't want to impress you with the pick and place application itself. The purpose of all this exercise was to show you how super fast, easy, and intuitive it is to program Sawyer, because you neither do need any programming experience. You do not need to be an expert for robotics. Really, anyone can learn to program Sawyer and yeah, collaborate with it. The end of our short presentation. I hope you enjoyed it, and I would like now to hand over the word to Hannes Koszynski, who's our innovations manager, and who will have a very exciting talk about artificial intelligence and machine learning. Thank you, Dennis.
All right. Thanks, Jessica, for the introduction. My name is Hans. Thanks for having me this afternoon. I hope you can hear me well, and I hope you are doing okay. Let me start a presentation. All right. Can you see the presentation?
Yeah, we can see.
Okay. Thanks. Cool. My name is Hans.
it's not-
I've been with Rethink Robotics for almost 2 years now. I'm a
Sorry,
mechatronic.
Hannes.
Yeah?
It's not in the presentation mode. We see PowerPoint itself, just to let you know.
Okay, hold on. All right. Is it working now?
Not yet.
So,
Okay. Well, I see it in full presentation mode, so I need some feedback, please.
it's not. It's still in the normal PPT mode. It's not in the presentation.
Maybe it helps if you stop sharing the screen and restart.
All right, let's try that. All right, let's try it from the start. How's it working now?
Yeah, it's fine.
No, it's perfect.
Okay, cool. Thanks. All right, it's working. So my name is Hans. I've been with Rethink Robotics for almost 2 years now. I'm a mechatronics engineer by training, and I also studied AI and machine learning, as I will talk about in a bit. And at Rethink Robotics, I'm responsible for innovations. So my job title is Innovations Manager, and I scout the latest trends and technologies on the market and anywhere else in order to help our company and look at our customer needs. Now, this talk is about AI, machine learning, and topics related. And let's take a look at how all these buzzwords differ. Let's start with AI. Artificial intelligence basically is a large, very large toolbox. And this toolbox contains a lot of techniques and methods and patterns that allow engineers to enable computers to mimic human intelligence, right? So this topic, this whole toolbox AI, it's very large, it's very broad, and any sort of, loosely speaking, any technique, any methodology that makes computers and robots smart in some way can be described as AI. Now, there's a subset of this large toolbox, and this smaller toolbox we call machine learning. And machine learning is a field of study that studies methods and patterns, instructions that allow engineers to come up with models that structure, classify data, and make smart decisions based on previous data. Okay, so let's try to wrap it up again. Machine learning is about generating models that make smart decisions based on data and algorithms, loosely speaking. Okay, and as part of this toolbox, there's another smaller toolbox. It's called deep learning, and deep learning is a field that has gained a lot of traction and attention in the last years, and we will look at some very cool applications in a bit. All right, let's dive into machine learning. And this slide shows a very rough overview with some of the most important algorithms in machine learning. And if you happen to be interested in machine learning, then I encourage you to read some articles about these methods, or even take some class or some master's degree in machine learning. Okay, let's look at some examples of machine learning algorithms. This picture right here shows the result of a data classification done by a so-called support vector machine, in short SVM, support vector machine. And this support vector machine basically distinguishes the data points into black and white dots by putting in some hyperplane, a line, a basic line in this two-dimensional space. Okay, so SVM is a nice classificator. It's heavily used out there in industry, research, and academia, and it can be used to classify and structure data points. This diagram shows a result of a classical line fitting and curve fitting, and some polynomial, some simple polynomial has been fitted through a whole bunch of data points. And this fits well. So one is able to predict, if this was some time series, some sensor data, for instance, then one would be able to predict what would happen in the future, since this curve fits these data points so well. Another method heavily used out there in research and industry is called the PCA, and that means principal component analysis. So again, we're looking, the algorithm takes in a whole bunch of data points. They are located somewhere in this n-dimensional space, and the algorithm gets applied, and it finds a whole bunch of clusters. These clusters contain similar data points with similarity. Okay, so this is the essence of machine learning. We use some methods. The machine learning engineer takes some methods, some approach. We feed data to these algorithms, and these algorithms, they are smart and they learn from the data. We don't tell these algorithms explicitly what to look for, but they themselves find what to look for and identify interesting key points and data points. All right, so this was a very broad overview of machine learning, and now we are diving into this cool topic called deep convolutional neural networks. Let's imagine for a second some task in the industry out there. You have a whole bunches, like in manufacturing, in the food industry, you have a whole bunch of pieces of cheese, right? And we have looked at this with some potential customer in the past. They produce thousands of pieces of cheese every day, and some human person and an inspector, if you will, some expert looks at these pieces of cheese every single day. Every few seconds, some piece of cheese comes by. This is a very, very strenuous task, right? So one could and should automate this task, and what we do is we might be using neural networks, right? So this is a structure of a typical network. It contains a whole lot of features, and these features are essentially matrices and vectors. And what we do is we feed a whole lot of images into the neural network, and they get processed in each layer. In each layer, some so-called convolution is being performed. That's a matrix. This matrix kernel gets multiplied with all these pixels. What comes out of that is a feature. That's another matrix or vector. And again, these features get processed with pooling. Take, for instance, the average or min-max or whatever. And then new features are coming out of that, new features, etc., etc. At the end, we have some very simple layers, so-called full connections. And then at the very end, what comes out of neural networks are probabilities. And that's what we're looking for. We're looking for classification of the images. And in this case, it could be damage detection, damage classification. And in one instance, the neural network might identify, okay, a specific piece of cheese contains mold on the surface, so it's bad. And because it's bad, it's got to be taken out of the production line. All right, and put away. Or in another instance, it might detect debris or crack, but we're dealing with probabilities. And this whole process, this whole network is being trained in many, many iterations. It takes hundreds, thousands, or even 10,000 iterations with tons of thousands of images. And what's being done is first forward propagation. We talked about this. The image gets processed. We receive the probabilities. If the results are not okay, if the probabilities are not correct and not what we expect them to be, then there is some error, right? Some difference between the expected probability and the like 100% for mold, for instance, and what we got out of the probability. Say that was 40 or just 30%. So we have an error. And then, thanks to some very simple formulas, there is a backward propagation going on, and this error gets backward propagated thanks to these formulas and algorithms until all these matrices and vectors that are essentially just numbers, so-called weights, are being adapted. And they're being adapted just right, or in such a way such that, again, in the forward propagation, the probabilities are okay. So we can work with them. And this whole process is called training. And after the model is being trained, new data is coming in, like real world data in day-to-day manufacturing. And then these pieces of cheese are being classified. And if something gets detected, pieces of cheese are taken out of the production line. All right. So this would be some very nice application in manufacturing. And on this side, and this slide, we will be looking at some more cool applications. We talked about image classification, image segmentation, labeling of images, right? These neural networks detect carbs, ingredients, fruits, vegetables, flowers, etc. But they might also be detecting street signs on the roads in public traffic. And these neural networks and these technologies, image classification on the road, is or will be heavily used in the cars of tomorrow. Almost all, as you probably know, almost all car makers are working on autonomous driving. And they might or probably will be heavily using deep neural networks that have been heavily trained with real world images on the road. You've probably seen some videos by Tesla, and they're large neural networks. Okay. Deep neural networks are also being used for speech translation and speech understanding. This slide, this diagram, excuse me, shows some results, some benchmark results for text understanding and question answering. So some AI models have been fed some text, some written text, and the model was then asked a question, and the model answered this question. And as you can tell, you can see these results for speech, text to text, and speech to text, etc., translation, understanding, get better every single year. So in the next couple of years or decades, these AI models, they will understand us humans very well. And at some point in time, we will be talking to robots or smartphones, intelligent smart devices in the factory, and robots like we are talking to a friend or other humans. And they will respond back the same way, or sort of the same way, as if we were talking to other humans. Neural networks are also being used for time series, like this diagram shows a typical instance of sensor data that's being heavily generated out there in factories and manufacturing plants by all sorts of machines. This data is large, is huge, and this data ought to be analyzed and processed to gain more insight about the processes. All right, the focus of this webinar is robotics and smart robotics. So let's take a look at how AI, machine learning, can and will be applied to robotics. This video shows some research that has been done, I think back in 2015 or 16, by the University of California at Berkeley. And they have taken some deep neural network and a technology called reinforcement learning, and we will explain this in a minute. And they have applied these technologies to a humanoid robot. The humanoid robot has a gripper, it has a camera, it has been given some tasks like hanging the hanger on the wardrobe, closing the bottle, putting some cube into the hole, etc., etc., and pulling the nail with the hammer, and none of the engineers and AI experts at Berkeley has told the robot how to explicitly solve this task. None of them has hard-coded how to solve this task. Instead, thanks to reinforcement learning, that's trial and error and repetition and lots of experiments, lots of trials, lots of failures, etc., the robot has entirely learned itself how to complete these tasks. And when I watched this video some years ago, I found it very, very impressive. Right now, it may take a lot of time to run all these experiments and go through all these iterations. So one could just do all of this in a completely virtual simulated environment. And NVIDIA has come up with some platform, some environment called ISAC. And what you could do is you could take the model of this humanoid robot and make it learn how to play ice hockey, right? And instead of just taking one agent or one robot, you use 100, right? And you run the simulation, the learning for 100 iterations or 1,000 or tens of thousands. Then imagine you take the best performing agent. You copy this best performing agent 100 or 1,000 times, and you repeat all of this learning until this specific task of playing ice hockey is being performed almost perfectly by the robot. That's the power of virtual reality and AI. Let's take a look at some more applications. This is a commercial application that's being used in the real world, in logistics, and in warehouses, at the assembly lines. It's a typical pick and place application. And Ozero, that's the name of the startup based in San Francisco. They have taken a robot, a deep neural network and reinforcement learning, and they taught the robot, or the robot taught itself how to pick all these objects, these meatballs, this specific example. And just think about it for a second. All these meatballs, they sort of all look the same, right? Like the pattern and the surface and the color and the shape, etc. But each individual meatball still is different and individual. And yet, the AI has learned how to grab all these objects, and it has taught itself how to grab these objects. That's the important part. Now, you probably have seen these very impressive videos by Boston Dynamics that go viral every year or so. And when I watched this video the first time, I found, and all of my colleagues, we found it very impressive how advanced their research is and how elegantly and how smoothly and how well these robots are doing and how well they are performing their task very precisely and stable, moving around, grabbing the boxes, putting them on the pallet, etc. It's just very impressive, and it shows you that that type of work, that's really the cream of the crop. It's the state of the art in robotics research, among other works, of course. This humanoid robot has been developed by a Japanese research institute, and this humanoid robot takes a piece of the wall, puts it on the main wall by screwing and hammering and fixturing. Honda used to have some robotics research program with the ASIMO, but they stopped it for some reason some years ago. And this sequence shows some humanoid robot by a startup called Preferred Networks, located in Tokyo, Japan. And they've used some deep neural network and taught the robot basically to clean up your living room, right? So it detects and identifies all these objects that you commonly find in the living room when you happen to have kids, or for some reason you're a messy person, then you might want to get one of these robots in the future, and it will help you to clean up your house. There's the Sawyer. We have looked at the Sawyer in the previous part of this webinar. And this is a typical application in manufacturing. It's called tannering. So Sawyer puts work pieces into the CNC machine and takes the objects out of the CNC machine after it's done. All right, we have looked at some very nice applications. Let's go back to some theory. And I would like to talk a bit about reinforcement learning. And reinforcement learning basically means learning by doing, learning through trial and error, right? Like we humans learn about our environment and learn about achieving certain tasks through trial and error and repetition and failure and success. Reinforcement learning, AI agents learn the same way. We have the environment, we have this agent with one or several neural networks, and the algorithm comes up with some policy. The policy generates some action. The action is being performed by the robot. It affects the environment, and some camera takes some observation, some images or video, and some reward is being issued, saying positive reward for success or some form of success, some level of success, or the whole process, the whole this instance failed for some reason, then this is penalty, so reward gets subtracted, right? And then the neural network takes all of this data, the images, the reward, and updates the policy at every iteration. And this whole process, this whole learning, trial and error learning process is being done for many iterations until this whole job is being done well by the robot. And there's Google DeepMind. You've probably heard of them. They're also the cream of the crop when it comes to AI research on this planet. And they heavily study reinforcement learning with the Sawyer robot. So they take deep neural networks, they take reinforcement learning algorithms, they put it all together, and they publish every year some papers about their top-notch AI research. And in this specific work and research, they made the Sawyer learn how to grab some boxes and to stack them on top of each other. And it may sound trivial to you, but it's not, because grabbing boxes is a tough job to do for a robot. It's a very easy job for us humans, since when we were 2, 3, 4 years old, we learned through trial and error and repetition and reinforcement learning ourselves how to grab these boxes and stack them on top of each other. But for the robot, it's a very hard job to do. And it takes a whole lot of software and hardware engineering in order to explicitly program and come up with some technical solution such that the robot would grab these boxes. But instead, here in this research, the Sawyer has learned itself entirely through simulation, reinforcement learning to grab these boxes. And here to play the ball in the cup game. Explicitly coding this solution would be very difficult and hard. The Sawyer has learned itself how to play this game, thanks to reinforcement learning and deep neural networks. All right. Google DeepMind has also looked at some assembly tasks, and they taught the Sawyer, this is a Sawyer robot, they taught the Sawyer to insert a USB key into a USB plug. And as you can see in the video, an engineer moves the PC slightly, and Sawyer has a camera here on top of the flash, recognizes where the new position of the USB plug is. And Sawyer has become smart, meanwhile, thanks to reinforcement learning, and puts the USB key into the right plug with the new and updated position. So this is a very nice application. I find this very interesting because these type of applications, this type of research will have tremendous implications in manufacturing and assembly processes in the real world in the years to come. I'm sure it will. Okay, let's take a look at the works by the University of California at Berkeley again. And they have also made the Sawyer learn some fairly complex tasks. And again, these tasks, they seem so trivial and so simple to us humans, since we have learned how to do these things when we were like 3 or 4 years old. But for a robot to achieve these things, to perform these operations, it's very difficult. And it takes a whole lot of hardware and especially software engineering and image processing and programming and all of that in order to get the job done. But thanks to reinforcement learning and deep neural networks, the Sawyer has learned itself entirely how to get the job done and perform these handling operations. All right. Now, I would like to talk a bit about ROS. ROS is a so-called robot operating system. It's a middleware, and we at Rethink Robotics use ROS a lot. And it turns out that Google DeepMind and the University of California at Berkeley also heavily use ROS to carry out their research. ROS has become a key enabler for reinforcement learning. ROS is a very powerful framework for the Sawyer and for us Rethink and for DeepMind, etc. Because it's very powerful. They heavily use it, and for us it provides a lot of advantages. Like the code gets structured, the code is easier and more flexible to maintain. You can use a lot of standard components, methods. The code is being kept at a modular level. The level of modularity is very nice, and it's better for testing code. And what you do is, if you as some robotics engineer want to work with ROS, you take these components, they're called nodes. You put the nodes together. On these nodes, they contain elementary building blocks, similar to Matlab Simulink or LabVIEW. These nodes, they contain parameters, tools, methods, data structures, and anything else that you need in order to run or design some program and run the program, right? So you take all these tools, you have all these capabilities, and ROS is being developed and maintained by a huge network of research universities and institutes all over the world. This whole network, this whole ecosystem basically acts as a global support system. So ROS is very important, and because it's such a powerful framework, it's heavily used by Rethink and DeepMind and others. When you use ROS, you don't have to worry about all these, say, robotic task, robotics components that you would have to develop and maintain yourself otherwise. So if you use ROS, it takes care of the coordinate transformations. It takes care of filters, for instance, the Kalman filter. It supports a lot of robot models. It takes care of perception, vision processing, mapping, SLAM, navigation, path and motion planning, and you're even able to simulate your robots. Okay, so now I would like to wrap up my talk, and I would like to do that by giving you some hints or some guidelines how you can get started if you're interested in robotics and if you're interested in AI and machine learning. So if you're interested in all these things and you want to get started, I would strongly suggest that you learn the programming language Python. It's very powerful, nice programming language. Then you go to Facebook, for instance. You become a member of the many groups that exist on Facebook on machine learning and AI, and you start reading articles about all these topics. The internet is full with material and content that you can read, or there are so many videos on YouTube about machine learning and AI that you can watch in order to learn all these topics. If you want to take it to the next level, you take a free or some affordable online class about machine learning at one of these online universities, Udacity, Udemy, Coursera. It turns out that I myself, I've taken 2 so-called nano degrees with Udacity, one about AI, one about deep learning. That's how I became familiar with all these topics. Then you might want to simulate the Sawyer and the robots, or you want to apply reinforcement learning to games in order to get started. So this link provides a list with powerful environments for running reinforcement learning. And these are some examples from the list. Then your next step, you want to study some papers by DeepMind, Berkeley, etc., in order to really dive into these topics and become an expert about deep reinforcement learning applied to robotics. And you at some point you want to make some simple example application run on your PC in a simulation. And you can download some examples. If you just Google long enough, you will find examples and source code out there in order to get started. You don't have to do everything all by yourself from scratch. Nope. There's lots of material out there and code and applications and models that you can already use in order to get started. And then at some point, you want to work with the Sawyer. You want to simulate the Sawyer, connect it with some AI, really do reinforcement learning yourself with the Sawyer in some simulation. And if you have managed to get this far, then congratulations to you. And if you happen to have some well-trained model with the Sawyer that performs some task, some handling task like this one, for instance, then you want to put this model on a real robot, such as the Sawyer, right? But my personal advice: start simple, right? These things are tough, right? They're not easy. So please start simple with simple models, simple tasks, small data sets, dive into machine learning, and then proceed with the level of difficulty, the level of abstraction, the size of your data set, etc., right? Okay. Here's another slide that will probably help you to get started with simulating the Sawyer. There's a free physics engine called Gazebo. You can download it, and it works with Python. And a software development kit by Rethink that the Sawyer uses, you can also download for free on GitHub. We provide it for free. And if you click on this link, you will find very specific guidelines and instructions on how to get started. And there's even a nice YouTube video I found that helps you to get the Sawyer robot up and running. This is a screenshot taken from this video. So you can, if you're interested in robotics and all these topics, you can get started today by clicking on these links and following these guidelines that help you to get started. Okay, that's it. Done here with my presentation. So I would like to thank you for your attention, and if there are questions, we might be able to answer them. Thanks.
So one of them is asking if they could get the PPT. Aman Arshad is asking that if you could get the PPT, if the participants could get the PPT that you just presented.
I have a hard time hearing you, ma'am, and understanding you.
Actually, Aman Arshad and few people are asking if they could get the PPT that you presented.
Oh, the PowerPoint presentation slides. We will
Yes.
discuss internally. We haven't actually talked about this before the talk, so
Yeah.
we'll discuss it internally. If the answer is yes, then we'll certainly share it.
If anyone has any questions or they would like to ask sir any doubts, they can write freely in the chat box. Feel free to write in the chat box and sir will answer your question.
Okay, so far people are asking for the PowerPoint presentation.
Can you use a complete simulation in Gazebo without using Matlab?
Okay, so
Can
the
you
question is if Gazebo can be connected or works with Matlab Simulink. I'm not an expert with Gazebo myself, so as far as I know, maybe not. Maybe not.
Okay.
Because
In
I
Matlab, without Gazebo in Matlab, can you use a robotic manipulator, a pick and place operation? Can you analyze the operation of pick and place?
I would have to look that up myself. I'm not an expert with Gazebo myself. I've worked with Matlab in the past, but I would have to look that up. Sorry.
Okay. Thank you. Thank you.
Welcome.
Sir, Sarath Manoj is asking how big is the company's client base as of now in the near future?
Okay, I think Florian or Jessica might be able to answer this question.
Yes, of course. I'm here. We have a client base worldwide. I mean, we are selling Sawyer since 3 years. And the product itself has a really long history. So we have clients all over the world, yeah, especially with the Hahn Group. We really hope with the new products coming up to increase our client base, of course, but you never know what's going to happen in the future. I hope that answers the question.
Thank you, sir. So Verena start. So thank you so much.
Thanks.
Thank you for this great effort.
Okay, thank you so much, sir. It was an honor to host, sir. It was an honor to host for you, and we would love that if we could have more future events. Now we would like to present a memento for. We would like now to present the memento to Mr. Florian Nadoli, to Mr. Dennis Trapp, and to Ms. Jessica Reosing. and Mr. Hans Kruszyniski. We would send this memento to you via mail and via LinkedIn. Thank you so much, sir. And it was nice to collab with IEEE Al-Safwa Institute of High Engineering, Egypt student branch. Thank you so much, everyone, for.
Thank you, sir, for this wonderful session.
Thank you very much.
Thanks for having us.
Thank you, sir.
Thanks for
Thank
having
you
us.
so much, sir. It was really an informative webinar, actually. Thank
Glad
you,
to hear that.
All right. All the best.
Thank you, sir.
Thank you. Bye.
Bye.
Okay.
Bye.
Bye.